cannot live another day without air conditioning.
Says tomorrow's gonna be hotter.
Hotter?
Like yesterday.
Yesterday.
Remember, atoms of uranium-238 can't be split readily. However, they do absorb neutrons. When this happens, a new fissionable element, plutonium-239, is created. So we can transmute a plentiful, almost useless material, uranium-238, into plutonium-239, another atomic fuel. And a breeder reactor, fueled with plutonium, can breed more plutonium. In the breeder reactor, a neutron strikes the nucleus of a plutonium atom. The atom splits. The energy is released, is used to make electricity. Neutrons are also released. A few strike fuel atoms, so the chain reaction continues. Other neutrons are captured by uranium-238 atoms. These become plutonium-239 atoms. And if conditions are right, we can breed more plutonium than is consumed as fuel. Though the breeder power plant principle was demonstrated in 1951, many engineering problems still remain to be solved before the breeder can go into commercial operation. For example, plutonium is highly toxic, so safety and security systems must be 100% effective to prevent accidents, theft, and sabotage. But both foreign and U.S. engineers see breeder reactors as one solution to the world's energy problem. What remains is perfecting their designs and safeguards. When that's done, we will have nuclear power plants that produce electricity, their own fuel, and fuel for still more reactors. Multiplying our atomic fuel reserves by 100, the breeder should provide the world with energy for thousands of years, far beyond all fossil fuel supplies now known. Beyond the breeder reactor, scientists and engineers are seeking energy from controlled nuclear fusion, the power that drives the sun. If fusion can be tamed, there may never be an energy shortage, for it runs off deuterium, an isotope of water abundant enough to supply energy for millions of years. Fusion depends on getting atomic nuclei called plasma to fuse together, liberating energy. But to provide energy to start fusion, the deuterium plasma must be heated to millions of degrees, while held together against its tendency to spread outwards. Fusion occurs in nature, for as each star condenses from gas in space, the pressure created by gravity kindles the thermonuclear fire, while the same force holds the nuclei together. Nobody wants a power plant the size of a star. The great problem for scientists and engineers over the past 20 years of fusion research has been how to contain the plasma. One answer is by applying a magnetic field to the ionized nuclei. So instead of straight escape paths, the charged particles move in spirals around the lines of force. In such a magnetic bottle, the particles might be held together long enough to fuse. Two types of bottles are under study. One is open but mirrored at the ends. In this system, strong magnetic fields reflect back particles which would otherwise escape. One test model is the SX mirror device at the Livermore Laboratory in Berkeley, California. In this experimental system, the plasma is injected into an empty vacuum chamber. The field is increased and the plasma trapped, heated, and compressed. The SX mirror device is operated at 2 million degrees. In a second type, the closed or toroidal bottle, electric coils wrapped around a donut-shaped container set up the confining field. The toroidal system, called tokamak, uses an electric current flowing inside the donut to hold the plasma together and heat it. The tokamak at Princeton, New Jersey has confined plasmas for 1/50th of a second at 18 million degrees. Computerized diagnostics chart the processes within. A magnetic bottle power plant might look like this. The hot plasma is held in a vacuum vessel. Lithium circulated around it is used to drive a turbine. A water jacket gives protection from heat, radiation, neutrons. This fusion plant should release no waste products and only minor thermal pollution. A second approach to producing controlled fusion is to fire laser pulses at deuterium pellets so their interiors implode into fusing plasmas. Soon this laser device at the Lawrence Radiation Lab will slam deuterium pellets with 10,000 joules of energy, generating implosions which should produce useful power. This future laser fusion power plant design puts the lasers in a circle pointing at a prismatic mirror. The laser's outputs are flashed by a spinning mirror over the prism through amplifier tubes to the pellet chambers outside. Again, the fusion reaction heats lithium, which drives turbines. This plant, too, is ecologically safe. Achieved by magnetic bottle or laser compression, fusion power will mean clean, safe, cheap electricity for millennia. Hopefully, man will soon be able to tame the stellar processes that have fascinated him for so long. But one fusion reactor is already operating, our sun. Each day, the sun delivers to the Earth's surface and atmosphere as much energy as man generates in 30 years. But to utilize it fully, we must overcome two drawbacks: bad weather and a low energy density of about 1 kilowatt per square meter in sunlight. One answer is to use solar energy to meet individual needs. This house has been heated by sun power for years. Air, warmed in these solar panels, is piped to the rooms. Likewise, the solar panels in this rolling lab allow the sun's rays to heat water circulated through them. Inside, a complete weather station and computers keep a record of the stored heat. The interior may be either warmed or cooled using this stored energy. The van will tour the U.S., mapping the nation's sun power potential. One sun power plant proposal is this solar power farm, collecting sun heat to boil a fluid which drives turbo generators. This plant would be coordinated with a hydroelectric dam to ensure that power would always be available. The temperature difference between the sea's sun-warmed surface and its cold depths might be utilized in this ocean thermal power plant proposed by Professor S.R. Hieronymus of the University of Massachusetts. In his design, warm surface water boils propane in these radiators so it drives a turbo generator. Then cold water drawn up from below cools and condenses the propane. The cycle is repeated endlessly, a fuel-less, pollution-less heat engine. Electricity for our satellites are increasingly being used here on Earth. Already they are powering navigation beacons and railway crossing signals. One bold proposal is to orbit huge arrays of solar cells, putting them in perpetual sunlight. Such arrays could produce up to 5,000 megawatts without fuel, moving parts, or pollution. The energy would be beamed to Earth via microwaves. Still other alternate energy sources are being investigated. An experimental motor has been built by engineers at West Virginia University to tap the potential difference between Earth and sky. With a balloon antenna, it can produce 6,000 volts. So far, collection devices can only tap a very little current flow, but a specially designed aerial may someday extract usable quantities of electricity from the atmosphere itself. Likewise, specially designed and located windmills like these, proposed to utilize the daily land-sea breeze, may supply power to individuals, villages, and towns. The rhythmic energy of the tides may also be harnessed, and currents like the Gulf Stream made to spin generators lined up across them in different parts of the world. But the energy challenge is much more than a group of technical problems. It requires that we choose a long-term energy policy, trading off energy usage against environmental when and where to apply our human and technological resources, reshaping aspects of our lifestyles. For the policy we choose will do much to shape the lives, hopes, and fears of our children, grandchildren, and succeeding generations, and the world they will have to live in. In the utilization of our energy alternates, we are not facing a problem. We are facing ourselves.